Hello everyone, here's another IB video. This time we're looking at simple harmonic motion of a pendulum and a spring system. So we're still deep into topic 9.1. This is the higher level content. There's quite a bit here that we've been going through. And the point of today is really just to show us that these two formulas are in fact true, they're real, they're derived from basic principles. So we're just going to be deriving these two equations. We've already done a lot of work on many of these ones here, and for today, we're definitely going to need a couple of these. For sure, we're going to need the acceleration one. So just keep your data sheet handy, and hopefully we can then go through and tick off a couple more. Okay, so here's a picture of a pendulum, and you may have seen pendulum analyses done before, where we look at this angle here, and then we start putting some force arrows, vectors on here to start forming an idea. We have to remember that at the back of our minds, we're going to be using our Newtonian dynamics. We're going to be using our F net equation. So F net being the sum of all forces, and that if it's accelerating, there's going to be an ma. We've also stated that we need to use an equation from our data sheet, which has previously been discussed and derived. That is the acceleration is the negative omega squared times the displacement. So we're going to be using this, and we're going to be matching it into there, into our F net equation. So let's take a look at some of the forces acting on a pendulum at a particular given instance in time. Let's focus on this moment in time here. Obviously the pendulum is going to be swinging back and forth, and if there's no friction, it will do this forever. If we imagine what's happening here, we can talk about the forces. So we're going to have a force acting on this ball that's going to be going along the line of the string. Okay, this is the force tension in the string. It's going to be pulling the ball up. If it wasn't for this tension force, the ball would obviously fall down. It wouldn't be in the simple harmonic motion of a pendulum. Okay, the other force to think about is the one that's going to be going straight down. Of course, this is our force of gravity. Okay, and then in this snapshot of time, of course, the ball itself is neither accelerating up along this plane or down along this plane. It's held in position by two equal forces. So I'm just going to draw in the force that would be equal and opposite to this red arrow, and this is going to be this force here. And if you can notice, hopefully you can see, this is actually a component of the green arrow. Okay, so if I carry on drawing this as a triangle, let's see if I can do it. Let's see if I can put this arrow here. Hopefully you can see that this represents a right-angled triangle, and therefore this second red vector arrow here is actually a component of the green one, and so it's going to be Fg cosine theta, because this angle here is the same as the other angle. These two shapes are geometrically identical. Okay, so we've identified an Fg cosine theta. We've identified an Fg. The other thing to mention is this black arrow. This arrow, is it balanced? Would there be another arrow coming up this way? Well, think about it for a second. This position represents the highest point of the swing. So at this moment in time, it's going to start coming back down this way. In other words, it is going to have an acceleration. It's a completely unbalanced force. So there is no force holding it in position. It's going to experience what we call a restoring force. This black arrow here is going to restore it back to its equilibrium position. And so this is an unbalanced force. Unlike the two red vectors that represent a balanced force, this one here is an unbalanced force. And again, it's a component of the green Fg arrow. So this is Fg, of course, sine theta. Okay, so let's relate this to our F net expression. We have an unbalanced system, if we're analyzing the restoring force of this pendulum that's coming back this way, we're interested in this Fg sine theta. That's going to be the driving vector force of our pendulum motion. So that's what I'm going to be using. It's an unbalanced force, so I'm going to say the whole system is undergoing an acceleration. Of course, we would have a mass in there, and that's going to be equal to the restoring force. So this would be my Fg sine theta, as we've just mentioned. So let's flesh this out a little bit more. We'll go ma, and that's going to be equal to the mg, because Fg is mg. So mg, and there we go, sine theta. Okay, so at this point, I think we can move our little vector diagram away. We're done with that for now. So let's just move this out of the scene. And at this point, we're going to need something else. We're going to need to, obviously, we're going to be combining, hopefully you can see we're going to be combining these two equations. But we also need to think about something called small angle approximation. So I'm just going to show you a little picture, a little graph from Wikipedia. So this is a small angle approximation, and it's a very important concept we'll see many times. So it's called small angle approximation. Oops. And what it tells us is that, and you can't really see it from here, but this x-axis would be 0 degrees, and at either end you'd have 90 degrees and minus 90 degrees. And so what you can see here is that on the x-axis, as you move away from 0 degrees, the tan, sine are essentially the same. There's no difference as you're quite close to 0 degrees. There's really no difference between these two, between these different functions. As you get further towards 90 degrees, the difference becomes significant. So what this means is that we can say, if we have a small angle, we can say approximately it means the same thing. Let me just make this case with some quick and dirty triangle diagrams. So let's go ahead and draw two triangles here. Apologies for not being perfectly straight. Let's put one here and one here. Okay, so let's go ahead and label these. This is going to be theta. Let's assume it's the same theta. I'm going to say that this is the length, and this is an x value. And what I can say here then is that sine theta is equal to x over L. Okay? What I can also do then over here, if this is L and this is x, I can also say that this is tan theta is x over L. And what's important here is that the differences, since this is coming from sort of some circles, right? This little difference here, let me just add it in, this little tiny little extra bit that is needed there. And of course, the same on this one. This, if this was here, oops, let me redo that. This, if this was a circle, this little tiny piece right here that would be needed to extend this triangle to make it a circle, these two extra pieces are just really small. And they're really small because we have a small angle. And this graph shows you how insignificant those pieces are. They're really insignificant. Effectively, it doesn't matter. We can completely ignore these differences. It's an approximation. So this is quite a powerful technique. If you've done calculus, it's kind of embedded into calculus, this idea of sort of infinitesimally small nudges or differences that we can kind of ignore. Okay, so that's really what we're doing here. If we ignore these little differences, we're basically saying that these triangles are the same thing, and therefore these statements are the same thing, which is quite powerful. So it means what we can do, we can say, therefore, if the, well, let's go small angle approximation, in other words, less than 10 degrees, okay, we can say that tan theta is equal to sine theta. Okay, how cool is that? This is a recurring theme. We'll see this in diffraction gratings. We'll see this in circular motion with banked corners. those kinds of things. It's a common theme. It's something useful to have up your sleeve, knowing that if we have small angles, we can interchange these functions. In fact, since I can say that pretty much any triangle can fit into this configuration, if I'm ignoring these tinsy little differences at the end, I can even go further and say that tan theta is equal to sine theta, which is also equal to, and I'll just add this on here, cosine theta. And that's relevant because when we chose our sine theta, we were using a triangle from the pendulum, but also that when we derived all of our simple harmonic motion equations, if you recall, we arbitrarily started with a sine theta function. But that was arbitrary. I just chose where to pick the starting point on the graph. I could have easily started with a cosine function, which would have given me different interchangeable ideas. And it's kind of the same thing with when we derived those equations, we interchanged sine theta, cosine theta, and that's because when they're at a function of 1, they're basically the same thing. So it's kind of a neat little trick that we're seeing again here. All we need to take away from this is that we're using small angle approximation. With a pendulum, we like to keep it under 10 degrees, and therefore we can interchange these ideas, which means we can now make a statement here. We can say that sine theta is x over L, and that's going to be important in the next step. Hopefully you can see we ended up with this statement here from our F-net expression. Hopefully you can see we're going to be inputting this acceleration formula in. And now also what we can see is that a sine theta can be represented as an x over L. Where have the x and the l's come from? Well, let's just take a look back at our diagram here. Maybe I want to say that the length of the string is L. So this would represent the L on the triangle. And maybe I want to represent this part of the triangle as x. That would be the displacement from the vertical point. Okay, I could do this in different ways. It doesn't really matter. The reason that we've just used our x and l is just to give you that geometric idea. Also remember that our data sheet, let's have another quick peek at that. Our data sheet is going to use, there it is, you can see, there's the L. Okay, so the x bit, not necessarily important for us to visualize at the moment, but the L definitely. In other words, the length of the pendulum definitely affects how it swings. It affects the periodicity of the pendulum motion. Okay, the other thing to think about is G. So let's see if we can get there. Let's do some derivation, and we'll take our three things together. Let's see if I can just circle them. We'll take our F-net expression, our acceleration formula, and our sine function, and we'll bring them together. So that's our job right now. Okay, so the first, let's start off with this MA is equal to mg. And now rather than using sine theta, because I've made a statement over here, I can just go x over L. So let's do that. So x over L. The other thing that's quite important here is, and again, you won't have to derive these yourselves, but just for the derivation, is to recognize the positives and negatives at this point. The net forces acting on the pendulum would actually be in the opposite direction. So we're playing this opposite game again that we did in some of our previous derivations. So I'm going to go and give the right side of my equation a negative sign. Remember this is the restoring force. So this would be, from the picture that we drew, this would be sort of to the left of the page. And this kind of makes sense because the F-net of the system initially was stated as being to the right, and then it's moving back again. So there's always this restoring force equal and opposite idea going on. Doesn't really matter for us, but just so that we know where that negative sign came from. And this next bit is really cool. Of course, the masses cancel out. And this was one of the observations by Galileo early on with this equation, or this statement, these principles were that the masses of the pendulums, or in Galileo's case, the masses of the chandeliers in the cathedral, they didn't seem to matter. So the big chandeliers and the small chandeliers all seemed to sway in the same way, irrelevant of the mass. So you can see that here with the equation. The masses just cancel out. So let's just rewrite this as a different statement. I'm going to say the acceleration of the pendulum is going to be equal to negative, and let's just go ahead and rearrange this differently just to give us a little bit more of a cleaner statement that we can use to get to our data booklet formula. So there we go, nothing special, just cancelled out the m's, rearranged it a little bit. At this point we can start plugging in the simple harmonic motion equation here. So let's go ahead and do that. So acceleration now is going to be equal to the negative, and again this negative came from that equal and opposite restoring force idea. Negative omega squared x is now equal to the negative g over L x. And so now you can see that this displacement piece is also cancelled out. That's kind of nice. So at this point I have to add a fourth equation that we probably have already memorized. We've seen this before. We know that omega is equal to 2 pi over t. So this is our fourth statement that's going to be part of this. Obviously you can see I'm going to be replacing this with omega. So let's go ahead and do that. Negative signs also cancel out. So we've got omega squared is equal to g over L. So let's go ahead and put in the 2 pi over t, of course everything being squared. So 2 squared pi squared over t squared is equal to g over L. Let's flip everything over, so we're just going to invert everything. So I'm going to say that t squared is equal to 2 squared pi squared is equal to L over g. Okay, and now I can just bring everything over. So I'm going to say that t squared is equal to 2 squared pi squared multiplied by L over g. And now what I can do is just square root everything. And that means I'm left with, let's do it over here, I'm left with the formula. T is equal to 2 pi square root of L over g. There's our pendulum formula. If you need to work out the period of a pendulum and you know the length of the pendulum, you're good to go. Gravity obviously is always going to be, on the surface of Earth anyway, is always going to be 9.81 meters per second squared, and you can solve problems now. Okay, so we found the pendulum formula right here. We're just going to have a quick look now at the mass-spring formula down the bottom. So where does it come from? Well, it seems only natural that we should start with our diagram of a spring. So here we have picture of our springs. Let's go ahead and imagine that this first one here is at rest. So this is just a resting spring system. So we can go ahead and just label a couple of bits on here. I'm just going to put a line through, dotted line through here, and call this the equilibrium. This is kind of the resting point, right? The equilibrium position. Then if I was to stretch this spring this way, I'm stretching it this way, you can see it's moving past that equilibrium point. And of course, if I let go of this spring now, assuming of course there's no friction, this is now going to return to the equilibrium position. In fact, it's going to return past the equilibrium position because of its inertia. It's going to go past the equilibrium position and it's going to go back and forth, back and forth, back and forth, essentially forever because we have no friction, because this is an ideal system. So let's just go ahead and label a couple of things. Let's put another mark on here. So if I take the center of here, you can see hopefully that the distance between here and, let's label it x, and here is x. This is the displacement, okay? Now the force, the returning force of this, actually let's use a different color just to make it clear. The returning force is going to be here, or the restoring force, if you like. The force restoring it is going to go here. We'll call this the restoring force. So let's just think qualitatively just for a few moments. Let's think about the different forces and different kinematics that are going on. Of course, at its zero displacement point, its equilibrium position, it's going to have zero force acting on it. Okay, because if it can just sit there forever if it wants to. As it's stretched out, if I apply a force, I can take it past its equilibrium position to any displacement I like, and then the restoring force is going to be proportional to how much I stretch it. In other words, if I stretch this a bit further, hopefully you can think about this in terms of springs or elastics. If I stretch this a little bit further, the restoring force is going to be bigger. Okay, it's proportional to the distance. So we can make some statements about that in a minute. In terms of kinematics, if it's bouncing back and forward in this simple harmonic motion, back and forth, back and forth, back and forth, as it reaches its maximum displacement, it's going to have temporarily, just momentarily at this point, zero velocity. Okay, so that's the change going from a velocity to the right of the screen. At this point, it changes direction and it's got a zero velocity before having a velocity towards the left of the screen. So all of those neat things going on. We've seen this with the pendulum as well. Exactly the same analogous situation, which is why we can still use those sine and cosine waves. We saw that at the very beginning of this with the flashlight and the shadow of the circular motion machine. It's the same idea. So let's just go ahead and make a statement at the top here. I'm going to be talking about this restoring force. So the net force acting on the object here as it's in motion, let's just go ahead and we can put this as a statement. So we're saying the net force acting on it here, hopefully you can see in green, is going to be the restoring force. So the force restoring. Okay, well, that's the only force acting here. So we have a Newton's second law principle happening. In other words, we do have an acceleration. The F net is not equal to zero. So we have an unbalanced force, which is where the ma comes from. We will have an acceleration. The maximum acceleration is going to be at this point here. And we've got Hooke's law. If we were to do this with a static spring system, we've already kind of mentioned it already, we can say that it's proportional. In other words, this restoring force is proportional to the amount you stretch it, the x value, but also this spring constant, this k. Now, just a thing on the positives and negatives again, of course, we can hopefully see that they're going to be opposite of each other. It's returning to its position, so it's that negative kx idea. Okay, so let's derive our equation. We're going to need a couple of things. We're going to need our displacement equation here that we got from our initial video, our initial lesson on simple harmonic motion. We did our sine and cosine waves and we derived using some calculus and we got these equations here. So we're going to need the first one. Let's just pick the sine. So let's go, we're going to need the x is equal to x naught sine omega t. Okay. The other one we're going to need is our acceleration equation, which isn't quite on this data sheet because if you'll remember that we ended up cancelling a bunch of terms out to get a simplified acceleration equation. But before we got to this simplified acceleration equation, we had this version. We had the acceleration of a simple harmonic system is equal to x naught, the maximum displacement, times omega squared sine omega t. Okay. Feel free to review previous video if you wanted to check that one out. But this is what we're going to be plugging into our equation. Hopefully you can see we're going to be plugging in the x into here and the acceleration into here. So let's go ahead and do it. Here we go. We end up with m and then the a is x naught omega squared sine omega t, and then that's equal to the negative k, the spring constant, times the displacement, which is x naught sine omega t. So all we've done is just put this into there and this into there. And there's a bunch of terms that can be cancelled out. X naught cancelled, sine omega t cancelled, which means we're left with negative k, omega squared, and m. So we can now say that omega squared is now equal to negative k over m. Okay, one more thing to add in. Let's put another equation over here that we already know. We know that omega is 2 pi over period. So of course what we're going to do is insert this into our equation as well. But before that, let's go ahead and just get omega by itself. So omega is equal to the square root of negative k over m. So at this point we can just get rid of that little negative sign. So k over m. We can do this, we get rid of the negative sign just because we want to be dealing with real numbers here, not irrational ones. And really the negative was just a communication tool about the vector, right? We were just defining which way the forces are going. So we're not too concerned about that here. We'll end up getting, we're looking for a period value, time value. So mathematically we have to get rid of it. Let's just leave it at that for now. So we've got our equation at the moment. We're going to insert our omega into this, and this nice and easy. You can see now that we get 2 pi over t is equal to square root of k over m. So now we just reciprocate everything and multiply by the 2 pi. So we end up getting our period by itself, and then 2 pi being, and then the square root of the reciprocal of k over m, which is m over k. And there it is. We've got our equation. We're now free to use these as we like. These very similar equations, look, the periods of these systems being equal to 2 pi square root of some sort of constant of the system, which in the pendulum would be the length of the pendulum, and in the mass spring it's going to be the mass of the object, divided by another constant of the system, the gravitational field being the constant in our pendulum, and then the spring constant in our mass spring system. All right, so for our worked example, we have a really cool technology here, accelerometers. Really simple idea, but basically you have a little enclosed unit, and then a mass sits within that closed unit. Normally it's, obviously this would be 3-dimensional and there'd be springs in all directions, but just to keep it simple, let's imagine we have a spring here and a spring here. And so this is going to measure the acceleration to the left and the right of the page. And we're told a few things. We're told that the mass is equal to 0.08 kilograms. We're given the spring constant K to be 4 kilonewtons per meter, okay, like this. And finally, we're told the amplitude of the mass is 20 millimeters. Now the question is, what is this amplitude talking about? Is this the maximum amplitude or just the amplitude? Well, to get at that, let's think about this system and let's think about it as a graph. So we've done this before. Let's imagine that we have time on the x-axis and amplitudes on the y. So this would be the negative amplitude. If this mass is stretched, so let's just draw another little box here and move it to one side. So there's a spring there, and then stretched out spring here. We'd be talking about the movement away from an equilibrium position. So this would be the x value in here. And so we could represent this motion with our graph. And let's just go ahead and start off with a sine graph. We could do either one. It's going to do this. This is the typical simple harmonic motion graph. And of course, this by default gives us these values to be the maximums. So if we start talking about this point here and this point here, those are going to be the maximum displacements. And it's at that point, the maximum displacement, that's going to be where the restoring force is at its maximum, which is where its acceleration is going to be at its maximum. So assuming in this situation that the amplitude of the mass is set up to be 20 millimeters, and assuming of course that there's no friction, then that will be by definition the maximum displacement, and that will therefore correspond to the maximum acceleration. So we can go ahead and put those values in, I think. We can say that at this point, the x naught, the maximum displacement, is 2 millimeters. In other words, 10 to the negative 3 meters. Okay, so then we can start trying to answer the question. In part A, we need to find the maximum acceleration. Well, we know from our equations, we know that acceleration is equal to the negative omega squared x. So let's go and put that in. So acceleration is going to be equal to the negative omega squared x. And I could put, if I know any value for x and any values for omega squared, I can work out the acceleration. What I'm saying in this situation, though, is that the maximum acceleration is going to be at the point of maximum displacement. So I could just as easily write this as a naught is equal to negative omega squared x naught, okay, because they are equivalent to each other. Now, I also know that at this point where the spring is at its maximum displacement, I know that there's an acceleration from my F net equation that's going to be equal to the negative kx restoring force. Okay, and then if I plug in my acceleration equation, I get to a situation where I can say that omega squared is equal to negative k over m. We've done this before, and this now gives me a reason to implant this part of my equation into this statement here. So I can get to a point where I can say the maximum acceleration is going to be equal to negative k over m and then x naught. So in other words, let's go ahead and plug these in. I can cancel out the negatives. The maximum acceleration of this spring system is going to be, let's put the numbers in, my k is 4 kilonewtons, so that's 4 times 10 to the 3 newtons per meter, and then that is going to be all over the mass, which is 0.08, and then multiplied by the displacement, which happens to be also the maximum displacement given that we've understood our system, and that's going to be 2 times 10 to the negative 3, in other words 20 millimeters. And so if I plug all that in, I get my value. Maximum acceleration is 1, and let me keep track of my decimal places and my significant digits. Looking up here, I've got 2, I've got 2, I've got 2. That means we need to report in 2s. So 1.0 times 10 to the 3, and that's an acceleration meters per second squared. Okay. Okay, so for part B, now we need to work out the frequency of the mass. Well, we know that the frequency is the reciprocal of the period, and we know the period appears in our spring equation down here. So let's just go ahead and write that out as well. So we know that the period of a mass spring system is 2 pi square root of the mass over the spring constant. And so here we're just rearranging and plugging in for our frequency. So pretty simple. We're just going to go ahead and do the reciprocal of this equation. So 1 over t, or 1 over period, is going to be equal to 1 over 2 pi of the square root of k over m. And of course, 1 over period is equal to frequency. So we can go ahead and just restate this to be frequency is equal to 1 over 2 pi, oops, not equals, 1 over 2 pi square root of the spring constant over the mass. And since we know all of those values, you can plug this into your calculator, and again, to 2 significant digits or 2 significant figures, you should get 36 Hertz. And that's it.